Hello and welcome to another NGen Math 6 lesson by eMath Instruction. Today we're going to be doing Unit 11, Lesson 8, Sampling a Population. This is our last lesson in our unit on statistics. And it's a very important lesson, right? Because it's all about populations and taking a sample out of them. Now this is what I would call a very experiential lesson. You're going to be doing this lesson and actually taking a sample from a quote, large population. And you're also going to be using samples that fellow classmates took from this population. So I'm really hoping you're doing this lesson right now in school. If you happen to be doing it with remote learning, we'll talk about that a little bit as well. But it will be helpful to be able to work with classmates on this lesson as well as taking data for yourself. Anyway, let's get right into it where we do a little sampling of a population. Now, statistics is used to answer questions about populations. You know, my favorite question that I've been returning to again and again in this unit is, how much money do lawyers make, right? And the population would be every single lawyer out there, right? Every single lawyer out there. All right, that's the population. But of course, if we really wanted to find out how much money lawyers make, we would have to take a sample of them, right? Because many times getting data from every subject in a population really is impossible. And if it's not impossible, it's really impractical, meaning that you could do it, but it would take a long time and really just be a pain, right? In those cases, we have to settle for a sample of the population. And remember, we want that sample to represent the population and not be biased. Let's take a look at that issue one more time in exercise number 1. If we were trying to answer the question, how tall are students in high school, why would taking a sample of 20 varsity boys basketball team members be biased or not representative of our population? What do you think? Pause the video now and see if you can answer this question. Now remember, you know, I might want to say, oh, well, on average, the students in my high school are 5 feet 9 inches tall, or something like that, right? So maybe I'm on the boys basketball team, you know, and I don't really want to go out and grab a really, you know, tough sample to get. So I just ask all my team members, you know, how tall are you? How tall are you? How tall are you? Right? Why would this sample be biased? Well, it would be biased because, number one, it's not random. And random means we just kind of grab people at random from the population, right? And it would be misleading because basketball players tend to be taller. Hello. Basketball players tend to be taller than the general population. Right? And this could be really problematic. Right? If I really wanted to answer the question, you know, how tall are people in high school? And I just use these basketball players, right? Maybe they come back and their average height is 6 feet 3 inches tall, right? And I said, well, on average, people in this high school are 6 feet 3 inches tall. That would be really misleading, right? That sample wouldn't represent the population at all. So when we take a sample from the population, we want it to be as random as possible, because if it is very random, it will make it tend to represent the population a lot better than if we have some kind of like, oh, well, I'm just going to take the basketball players, or, you know, maybe I'm just going to take the gymnasts, or maybe I'm going to take all the people in honors English, you know. I don't want to go there, right? I want it to be random. I want it to be every 8th person that walks in the door, or something like that. So we're going to take a look at how we can find random samples from a population in this lesson. All right, so let's take a look at our population. Exercise number 2. A population of 200 heights of students in high school, in inches, is shown in the dot plot below and in Table 1. There's a lot of sheets to this lesson, by the way. This population includes 100 girls and 100 boys. The median height is 67 inches. Letter A, the distribution has 2 fairly distinct peaks. At what heights do they occur? All right, so just a little bit of terminology, the idea of a peak. Why don't you pause the video now and tell me where the two relatively distinct peaks of this data distribution occur. All right, well, there's one here and there's one here. The one here occurs at 65 inches, right? And then the one here occurs at 70 inches. So pretty much two very kind of distinct peaks. And why do you think there are two distinct peaks? That's letter B. It's all about context. Why do you think there are two distinct peaks? Well, there's probably one likely for girls and one likely for boys. Now that doesn't mean that, like, you know, every boy is taller than every girl, or vice versa. You definitely probably have some boys down here and some girls up here. But generally speaking, boys tend to be a little bit taller than girls, especially by the time you reach high school. All right? So one peak for girls and one peak for boys. All right, kind of interesting, right? Now, more terminology. It's a great chance for us to review some things. What is the range of this population? Pause the video now and calculate the range. Well, the range is the width of our data set, right? And it's measured by finding the lowest value here at 50, the highest value here at 84, and finding their difference. So the range is equal to the maximum value minus the minimum value. That's going to be, let me just make sure, 84 minus 50, or 34 inches. By the way, think about that just for a moment, right? 36 inches is 3 feet, right? So 34 inches is pretty close to 3 feet, which means there's a 3-foot difference, almost a 3-foot difference between the shortest person in this high school and the tallest person in this high school. Kind of pretty cool, right? That's what the range tells us. Now, letter D, a little bit about shapes of the distribution. Is this population uniformly distributed, symmetrically distributed, or neither? Explain. All right, pause the video now and tell me what you think. All right, well, one thing I can say for certain, it is definitely not uniformly distributed, right? Again, a uniform distribution would mean that each one of these like dot heights would be the same. You know, there might be 5 dots, 5 dots, 5 dots, 5 dots, 5 dots, 5 dots, etc. This is definitely not uniformly distributed, all right? I would say it's not really symmetrically distributed either, although it's certainly closer to being a symmetric distribution than it is to being a uniform distribution. But a symmetric distribution would mean that it looked exactly the same on this side as it does on this side. So I would actually say neither, because there are different, let's try to do different there. Different numbers of data for each category. Well, I'm going to say for each height. And it doesn't look the same on the right as it does on the left. Now, I think it would also be completely acceptable for this particular problem or this particular question to say, well, it's almost symmetric. You know, there is a decent amount of symmetry, right? Because it tails off down here. There's fewer people down here that have much shorter heights, and there's fewer people down here who have much taller heights. I still don't think it's symmetric because, there's very few people that have very high heights down here, just one dot above each one of these. Whereas down here, you get, a decent amount of people that are actually kind of at these sort of shorter heights, if you will, right? So I still don't think it's symmetric, but if your answer to letter D was that it's nearly symmetric because it kind of looks the same on the left as it does on the right, I think that would be an awesome answer. I don't think there's anything wrong with that. One thing about statistics is that often there isn't just one right answer. The answers are more what are known as nuanced. There's a little more kind of give and take in them. Anyway, welcome to our population, right? Now what we're going to do is start to take systematic, random samples from this population. Now, how are we going to do that? All right, let's talk about it. Because finding a random sample from a population can be a little bit tricky. So let me explain how I designed it in this lesson. First off, you've got table 1, and table 1 shows you the heights. Now, I want you to keep in mind the heights are sort of in the columns that are shaded white, all right? The numbers that are in the columns that are shaded gray, those are actually just which data value it is. So in other words, the first data value is 70 inches. The second data value is 59 inches. The third data value is 68 inches, all right? That's what the grays are. The grays aren't heights. They're just like, hey, 1 to 200, all right? Now, what we're going to be doing is I want each one of you to take a random sample of 20 values from this population. Now, here's how you're going to do that, all right? Besides table 1, which shows you the heights, you also have table 2. Now, table 2 has just a ton of random numbers in it between 1 and 200. All right, remember we have 200 heights. So all the numbers in this table, and this just shows you a small picture of the table, all of them in this table, right, are numbers between 1 and 200. So what I want you to do is I want you to go down to the numerical date of your birthday. So I was born on December 28th, all right? So I would go down to 28, and this would be my row. Now in this row, there are 20 numbers, random numbers from 1 to 200. 20 random numbers from 1 to 200. These are not the heights, all right? These are not the heights. What these are where I'm going to get the heights. So given that table, you want to have table 2 and table 1 just kind of sitting in front of you, right? And here's what you're going to do. So like the first number for me is 136, 136. So I'm going to go into my tables of heights. I'm going to find the 136th number, and that happens to be a height of 70. So these aren't my heights. These are where I'm going to go in my height table to get my heights. So I've got height number 136, and that happens to be 70. Then I've got height 106, so I go to where 106 is, and that's 61. So I get a height of 61. Then I go to the 66th number in my table. I gotta watch out because 66 almost seems like it's a height, but it's not. All right, and that gives me a height of 73, right? So these are the first 3 heights that I randomly sample from the height table based on this row of 20 randomly generated integers between 1 and 200. And that's exactly what I did. I just used a spreadsheet to fill this table with just tons and tons of random numbers that go from 1 to 200. So what you're going to do is you're going to pick your birthday. If you were the 17th, like October 17th, you'd want to go to number 17, and you'd want to go along that row with table 1 and just keep picking these numbers, going into the table, and coming up with the heights that are associated with them. Now that's going to take you a little while, right? That's going to take you some time to do. All right, so take some time, do it, and write down your sample, your random sample of 200 numbers. Pause the video now and take some time. Now, I can't do this for every one of the 31 rows in this table, all right? I can only do it really for my own. And What were mine? Well, they were these, right? We already knew what my first three numbers were, 70, 61, and 73. But these are all of my 20 randomly selected heights from my population, okay? And if you're lucky enough that you were born on January 28th, February 28th, March 28th, whatever, if you were born on the 28th of some month, then you're going to have exactly the same 20 numbers that I do, okay? If you were born on some other day, you're going to have 20 other randomly selected heights, all right? But whatever your heights are, then let's move on to exercise number 4. Let's take a look. Create a dot plot of your sample below. Then find the A, median, and B, the range of your sample, all right? So I'd like you to pause the video now. If you got the same sample as mine, awesome. Your dot plot's going to look the same, your median's going to be the same, your range is going to be the same. Unfortunately, obviously, if you have a different sample than I do, you'll have a different dot plot, a different median, and a different range, okay? But that's okay. That's okay, right? I will show you a few other ones as we go on, but this is the one for those born on a 28th. All right, pause the video now and go ahead and make the dot plot, find the median, and find the range. Now, this could be a little bit of a challenge, right? Here's my dot plot distribution, but it could be a little bit of a challenge because for the first time, you have a data set that is not in ascending order. It's not in order. So finding the median is more challenging. Let's talk about how to find the median if you've got a dot plot. Now remember, I've got 20 values, okay? N equals 20, all right? So if I take 20 and I divide by 2, I obviously get 10. Now think about this for a minute. That means that the median, right, is actually going to be the average of the 10th and the 11th value, right? So the median is going to be the average of the 10th and 11th values. So how do I decide on what those are? Well, I start counting some dots. Watch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is my 10th value. And this is my 11th value. You could also count from this direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in which case that's my 10th value and that's my 11th value. It doesn't matter. My 10th value, right? My 10th value for me, my 10th is 64, and my 11th value is 65, right? So my median is going to be the number immediately between these two, which ends up being a decimal. That's okay. We're good with that. And my median is going to be 64.5, right? The number that's halfway between 64 and 65. You may have come up with a median that was a nice whole number, right? In fact, your median will oftentimes be a whole number if the 10th and the 11th value are the same number. So if the 10th and the 11th value for you were both 66, then the median is 66. If your 10th and 11th value were both 62, then your median is 62. For me, unfortunately, my 10th value is 64, my 11th value is 65, so when I average them, I get 64.5. Now the range is a piece of cake, right? Because for me, I can see my minimum is 50 and my maximum is 74. So my range, I apologize for this getting a little bit messy in here. My range is going to be my maximum, 74, minus my minimum, 50. So it's going to be 24. Right? And both of these really have the units of inches on them. So my median is 64.5 inches, and my range is 24 inches. Now, before we even move on, right, the whole idea of sampling, taking a sample from a population, is that you hope that your sample will represent your population well enough that I could now say, well, even though I don't know the whole population, probably the median is close to 64.5, and we'll talk about the range in a little bit. All right, because that's a little different. Anyway, exercise number 5, let's take a look. How do your median and range compare to those of the population? Give the values for both, and then state whether your sample would underestimate or overestimate the value of the population. So again, almost never can I actually figure out the population statistics. It's almost never the case that I can actually get the population median and the population range. Here, I told you them up front, okay? So, well, actually, I told you what the median was, and then we calculated the range, right? So we can actually compare them to our samples themselves. So that's what I want you to do. For the median, put the population median in, go back to the first page if you don't remember what it was, then put your sample median in, and then tell me whether your sample overestimates the population, right, if your sample's bigger than the population median, or underestimates it. And then for the range, give me the population range, give me the sample range, and then tell me whether the sample range is an over or an underestimate of the population. All right, pause the video now and go ahead and fill these blanks in. All right, well, let's do it. All right, so the population median was 67 inches, which I told you, and my sample median was 64.5. And therefore, my sample median was an underestimate. All right, it's not too far off, right? I mean, it's not like, you know, my median was like 61 inches and the population was 67, or maybe my median was like 82 inches and the population was 67. Like, it wouldn't be horrible if I said, well, it appears that the median height is around 65 inches. That wouldn't be terrible, right? Because it'd only be a couple inches off. Now, look at the range. The population range is 34 inches. My sample range was 24 inches. This is also an underestimate. I kind of wish one of them would have been an overestimate, but what can you do? I was born on the 28th, so that is what it is. And that's an underestimate. Now again, we'd like to be able to use our sample statistics in order to kind of talk about our population statistics, but consider this question in letter C. Could the range from a sample ever be larger than the range for the population? Explain. Could the range from the sample ever be bigger? Could it ever be an overestimate than the range of the population? Explain. Pause the video now and consider that very important question. Absolutely not, right? Now, that has nothing to do with the median. We're just talking about the range, right? Now, why is that? Why is the range of a sample have to be or can't be larger than the range of the population? Well, think about what range is, right? Range measures the width of a data distribution, right? That's what range measures, right? Since the sample comes from the population, it can't have a larger width. And think about it like this. Think about a population as being a board, right? Think about a population as being a board with a certain length. And think of a sample as being a piece of that board, right? With the range being how long the two boards are, right? You know, it could be that the sample is as wide as the board itself if you took the whole board, right? But there's absolutely no way, right? There's no way for that piece of the board to get bigger than the total board, right? Now that's still helpful though, because if we took a sample and we found that its range was 24 inches, like I did for my sample, then I would know that the range of the population had to be bigger than 24 inches. Now the median The median of the sample could be higher than the median of the population or lower than the median of the population, but one thing I know for certain, the range of the population must be greater than the range of the sample. It just has to be. So, what do we really want to do now, right? The plain fact is, your sample probably had a different median and range than my sample did. So let's take a look at what I'd like you to do in exercise number 6, if you even can. Work with 3 other classmates to come up with 4 total sets of sample data. All right? Now, again, I don't want you to literally write down their samples of data. I just want you to find 3 other classmates if you're working in a class, if you're not working remotely from home, or if you are working remotely from home and you know other friends who are also working on this, maybe send them a text. Worst case scenario, just pick 3 other rows in that random number table and redo all those samples. I know that would take a while. It's not what I intend for you to do, but to really get the point, you could do that, all right? Pause the video now and collect some additional information from other people who've done this experiment. All right, well, for me, I did this myself, all right? Now, just for the record, right, I took it from the 28th, corresponding to my birthday. I also took row 6, corresponding to, January 6th, February 6th, whatever. I also took row 13 and row 21. So if you have a birthday that is the 6th, the 13th, the 21st, or the 28th, you can actually check your numbers with mine, all right? And I found the row 6 had a median of 68, a range of 20, right? Row 13, median of 69, range of 12, 68, 25 for row 21. Remember, right, the population mean, for the population, we had a mean of 67, and what did we have? We had a range of 34. Anytime I switch screens, those numbers disappear. That's okay, we can always make them reappear. And remember that observation we made in the last problem? None of these sample ranges are larger than that population range. And yet, the medians, right, you've got mine, it's below the population. The other 3 actually ended up being above the population median. In fact, that kind of answers exercise number 7. Were any of the medians in the table above equal to the median of the population? And the answer, at least for the 4 I did, was no, but they were all relatively close. All right, and they were all relatively close because we did a nice systematic random sample. In fact, mine, for my birthday, was actually farther away than any of the others. These are really quite nicely close, right? 68, pretty close, right? The 69, a little bit farther away, again, another 68 there. And obviously, right, all of these medians are reasonably representative of the population median. All of the ranges, of course, aren't, because the range of a sample must be smaller, or it certainly can't be larger than the range of the population. Now let's take a look at one last little facet, okay, which is what's called sample size. Take a look at exercise number 8. Let's double the sample size to 40 instead of 20. A random sample of 40 heights from our population is taken and graphed on the number line below. Letter A, find the median of this sample. How does it compare to that of the population? All right, go for it. You got to find yourself a median based on a dot plot. Now I've got 40 of them up here, right? So think about how that works out in terms of finding the median. Pause the video now and see what you can do. Well, again, if I took these 40 heights and I lined them all up in numerical order, right, then the median, there'd be 20 below the median and 20 above the median, right? And therefore, the median would be the average of the 20th and 21st data point, right? That's how I would find the median. I'd average these two. All right, so what am I going to do? I'm going to go over here and I'm going to carefully count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Right? These are the 20th and 21st. And what are they? They're 67. So since both of these are 67, right, the median is 67. Okay, awesome. Now for letter B, find the range of this sample. Is it closer to the population range than our samples of size 20? All right. Ooh, I didn't compare this. I left something out. How does it compare to that of the population? It's the same. Same as the population, right? The population median was also 67. Now I want you to find the range of this population in letter B and compare that to the population range as well. Pause the video now. All right, well, here we go. Right, here I've got 81 as my max. My min is 53. So my range is going to be 81, let me just make sure, yep, minus 53. Right, and that's going to be a range of 28. All right, now my other ranges, right, 24, 20, 12, 25, right, this range has now gotten larger. Not a lot larger, but it's definitely closer. Yes, closer to population range, right? So the median, I hit the population median right on the nose. Now remember, I'm only taking 40 of the data points out of a possible 200, right? So I'm still taking a relatively small sample compared to the population. But the final important piece, letter C. Generally, how does the size of a sample affect how well it represents the population? Well, think about this and write something down. Okay, well, generally speaking, the larger the sample size, the better it will represent the population. All right, and in advanced statistics, you get into kind of all these different like rules of thumb for, well, if the population is this big, you want a sample size of at least this much, et cetera, et cetera. Generally speaking, statisticians always like to stay away from sample sizes that are smaller than 30. So, you know, those samples we took of 20, maybe not the best, but a sample of 40, pretty good, right? And it makes sense. I mean, think about it this way, right? The smallest sample size you could possibly make is a sample of 1. Right? Now, that would be horrible, because if you just went to those 200 heights and you grabbed a single person and you said, oh, that's my data set, there's my sample, you know, you could end up picking somebody who's really short, who's really tall. You could end up picking somebody that's got the perfect median height, but I'll tell you, the range is going to be 0 in that case because there's only one height. So the max minus the min is going to be nothing, right? The other extreme is, of course, you sample the entire population. You take all of them, in which case the sample and the population are the same, and therefore it's going to represent the population perfectly. But the big point here is, right, if you want a sample to represent a population in terms of measures of the center, like the median, and measures of variation, like the range, then you want to make the sample size as big as you can, as big as is reasonable, all right? And the bigger the sample size, the better it will represent the population statistics as a whole. All right, let's wrap this up. In fact, I kind of did just wrap it up, right? In statistics, we are always trying to answer questions about populations, but it's very rare that we can get a data point from every subject in a population. How much do lawyers make? There's no way I can get the salary of every single lawyer. There just isn't any way. So I go out and I randomly select 500 lawyers and I ask them what their salaries are. And that sample will hopefully represent the larger population of lawyers. And I want to make sure I take a big sample, because if I go out and I just find 5 lawyers and I ask them how much money they make, well, it could end up being that their average amount is representative of the average of the population, or it could be that I, randomly picked 5 lawyers who make much less money or much more money than the population of lawyers as a whole. All right? So sampling a population is critically important in the branch of statistics, and in fact, almost all statistics we ever do are on samples and not of populations. You're going to work a lot more with this as you move forward in Math 7 and in high school statistics work. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.